Here, vector of rectangular sin x divided by x and triangular pulses in frequency domain under rectangular pulses and its spectrum. Already we have seen minus 3 by t to 2 by t. Here 1 t TSA of pi TF. This is an example. SAX pulse and its spectrum. Here time domain 2W SA of 2 by F 2 by WT minus 3 by 2 W minus 1 by W minus 1 by 2W 1 by 2 by 2W 1 by W T equal to here W 2W SA of 2 by WT. So this is example in time domain SAX pulse and its spectrum. Here in frequency domain minus W plus W height 1 F frequency x axis W by F divided by 2W. Triangular pulse and its spectrum. In time domain triangular of t by t height time domain minus t 1. Here minus 3 by 2 minus 2 by t minus 1 by t 1 by t 2 by t f 0.5 t 1 t t SA square of 5 t f. Spectra rectangular sin x divided by x and triangular pulses. Spectra of a triangular pulse omega of t equal to triangular tt by tt triangle of t by t small t by capital T. As omega of t equal to triangular of small t by t implies t SA square of pi f t. Conversion represents the conversion of a waveform omega t is with the waveform omega 2t omega 1t with omega 2t to produce third waveform is W3t. W3t equal to omega 1 omega 3 of t. Omega 3 of t equal to omega 1 of t conversion omega 2 of t equal del minus infinity plus infinity omega 1 of a lambda omega 2 of t minus lambda t lambda, where omega t and omega 1t and omega 2t is a shorthand notation for this integration operation. Star is real conversion with t. So omega 3t equal to omega 3 of t equal to integral of minus infinity plus infinity omega 1 of lambda omega 2 of minus lambda minus t t lambda. Conversion of a rectangle with an exponential. Omega 1 of t equal to pi of t minus 1 by 2 of t by t and omega 2 of t equal to t e power minus t by t u of t. Conversion of a rectangle and an exponential. Lambda minus t t 2t height 1 omega 1 of lambda omega 2 of lambda minus t t 2t lambda. Okay, this is the matter. Here omega 2 of minus lambda minus t minus t, small t, capital T, 2t, lambda. W3 of t after conversion t 0.63t minus t plus t 2t t. So conversion of a rectangular to exponential. Rectangular and exponential. Spectrum of a triangular pulse by conversion. Spectrum of a switched sinusoid. Omega of t equal to pi of t by t, a sin omega t equal to pi of t by t, a cos omega t, omega naught t minus pi by 2. Waveform and the spectrum of a switched sinusoid. Waveform and the spectrum of a switched sinusoid. Here, in time domain, here from here in this waveform 1 by f naught. The total t. This in y-axis omega of t. A height waveform amplitude is A. This is the in time domain. Here frequency domain magnitude S spectrum waveform spectrum of which is inside. So here 1 by f naught will be between here. That is here. 1 by f naught. Here 1 by t from here up to here minus f naught here. Mod of W of f a by at by 2 0 here 1 by t here. Mod 1 by t f. This is time domain, this is frequency domain. Waveform and the spectrum of inside. Power spectral intensity here the frequency domain we have seen W of f equal to W1 f conversion with the W2 f equal to integral over of minus infinity to plus infinity W1 of lambda W2 of f minus lambda into here power spectral intensity the autocorrelation function power spectral intensity some Fourier transforms pairs function time domain omega of t spectrum omega of f rectangular pi of t by t t of sa of pi f t triangular t by t t of sa pi f of t whole square unit step u of t del equal plus 1 t is greater than 0 at 0 condition t is less than 0 in spectrum 1 by 2 del of f plus 1 by j 2 by f signum sin sgn of t del equal plus 1 t is greater than 0 minus t is less than 0 in the spectrum omega wf 1 by j by f constant impulse at t equal to t0 1 del of t minus t0 here del of f e power minus j 2 pi f t naught sinc s sin c sa 2 pi omega t wt 1 by 2w pi of f divided by 2w here phasor e power j of omega naught t plus pi e power j pi del of f minus f naught sinusoid cos of omega c t plus pi 1 by 2 e power j pi del of minus f by fc plus 1 by 2 e power j minus j pi del of f plus fc Gaussian e power minus pi t naught whole square t naught e power minus pi of f t naught square exponential one side e power minus t condition t is greater than 0 if 0 condition t is less than 0 in spectrum w of f yes f naught summation of minus n equal to minus infinity to plus infinity del of f minus n f naught where f naught equal to 1 by t. Autocorrelation function. Related function called autocorrelation r of tau can also be defined. Definition: the autocorrelation of a real physical waveform is r omega of tau del equal omega of t into omega of t plus tau equal to limit t tends to infinity 1 by t minus integral over minus t by t to t by t omega of t plus tau t r omega of tau implies p omega of f. Direct method, indirect method. By using definition equations, power in indirect method p omega of f equal to f of r omega of tau p of omega square of t equal to omega w square rms equal to integral of minus infinity to plus infinity p w f of df equal to r w f 0 p s of s sinusoid omega of t equal to a sin omega of t. Then we get power spectrum of a sinusoid minus f naught plus f naught in f x-axis p of f a square 4 here up to here height a square 4 this weight is a square by 4. This value a square by t checks with the known result for the normalized power of a sinusoidal p equal to omega square of t equal to omega square rms equal to a divided by root 2 whole square equal to a square by 2. Omega of t equal to summation of minus n equal to 0 to infinity omega of n into n factorial into t power minus a power n where omega power n a equal to mod of t d power n omega of t by t power t n t equal to a. Orthogonal series representation of signals and noise. Orthogonal function. Before the orthogonal series studied define orthogonal functions. Functions where function phi n of t and phi m of t are said to be orthogonal with respect to each other over the integral a tends to p, that is a less than t, t is less than p. If they satisfy the condition, integral over a to b phi n of t conversion here will come here phi m of t dt and equal to 0 where n equal to not equal to m. Orthogonal complex exponential functions. Orthogonal series theorem omega